What's the actual difference between Docker and Podman? How's Containerd really different from CRI-O? From the runtimes you fire up on a laptop in 30 seconds to the ones quietly holding up half the internet, the container world has way more layers than most people realize. So today, we're going to walk through every container runtime worth knowing about, ordered from the simplest, closest to the metal piece of software, all the way up to the full-fat platforms running global infrastructure. We'll break down what each one actually does, who it's built for, and which ones you'd ever touch yourself. So let's start at the bottom of the stack, with the smallest piece of the puzzle. First up is runc, and runc is so foundational that most people using containers every day have never typed its name once. It's a tiny command line tool, written in Go, that does exactly one thing. It takes a container configuration and actually starts the container. That's it. It talks to the Linux kernel, sets up the namespaces, configures the C groups, drops the right capabilities, and hands you a running process. The binary itself is around 15 megabytes. It has no daemon, no API, no networking, no image management. It's the engine block of the container world, and like an engine block, you almost never look at it directly. When you run Docker, Containerd, Podman, or basically anything else in this video, runc is the thing actually doing the work underneath. It came out of Docker's original container code back when the company donated the low-level bits to a standards body, and it's now the reference implementation of the OCI runtime spec. If you ever want to feel how thin a container really is, you can use runc by hand to start one from a JSON config file. It takes about 3 lines. Runc is the distro that quietly runs more of the internet than anyone gives it credit for. Except it's not a distro, it's a runtime, and nobody gives it credit at all. Just above runc sits crun. Same job, completely different personality. Crun is a rewrite of runc in C instead of Go, and the headline number is brutal. It starts containers roughly twice as fast as runc, uses a fraction of the memory, and the binary is closer to 1.5 megabytes. On a laptop, you'll never notice. On a node spinning up thousands of short-lived containers a day for serverless workloads or CI jobs, that overhead becomes real. Red Hat has been pushing crun as the default in their container stack. And if you're on a recent Fedora or RHEL system running Podman, you're almost certainly using crun without knowing it. It's the specialist of the bottom tier. If your exact problem is, I'm starting and stopping containers thousands of times a minute, nothing else really competes. Moving up the abstraction ladder, we hit Yuki. Yuki is the new kid, written in Rust, and it exists for roughly the same reasons every Rust rewrite exists: memory safety, performance, and the deep satisfaction of writing it in Rust. It implements the same OCI runtime spec as runc and crun, so it's a drop-in replacement in theory. In practice, it's still maturing, the ecosystem support is thinner, and you're unlikely to see it in production unless you're at a company that specifically wants to bet on Rust in the container stack. It's worth knowing about because it tells you where this layer of the stack is heading: smaller, faster, and written in languages that don't let you accidentally corrupt memory at 3 in the morning. Now we step up a tier. Above the low-level runtimes sit the high-level runtimes, and the first one is Containerd. Containerd is the layer that turns a raw runtime into something usable. It manages images, handles pulling them from a registry, sets up storage and snapshots, configures basic networking, and coordinates the lifecycle of containers as they start, stop, and get cleaned up. It runs as a daemon, exposes a gRPC API, and underneath it calls out to runc or crun to actually start the processes. Here's the part most people don't realize. Containerd is what's inside Docker. When you install Docker today, the engine you're using is largely a friendly wrapper around Containerd. Docker spun Containerd out as its own project years ago and donated it to the Cloud Native Computing Foundation, and it's now the default container runtime for the vast majority of Kubernetes clusters running in production. AWS, Google Cloud, Azure, basically everyone runs Containerd under the hood. If you've ever pulled a public image to a managed Kubernetes node, Containerd was the thing fetching it. It's the workhorse of the modern container world, and like most workhorses, it gets approximately 0 credit for it. Sitting right next to Containerd is CRI-O. CRI-O exists for one specific reason. Somebody at Red Hat looked at the Kubernetes container runtime interface, looked at how much general-purpose stuff Docker and Containerd were doing, and asked whether you could build a runtime that did the absolute minimum required to run Kubernetes pods and nothing else. CRI-O is that runtime. It implements the Kubernetes CRI directly, calls out to runc or crun underneath, and refuses to grow features that aren't strictly needed for Kubernetes. It's the default runtime in OpenShift, which is Red Hat's enterprise Kubernetes distribution, and it ships in a lot of the security-focused Kubernetes setups. The pitch is simple. A smaller surface area means fewer bugs, fewer CVEs to patch, and a tighter relationship with the kernel features Kubernetes actually uses. Containerd and CRI-O are basically competing philosophies for the same job, and which one you end up running mostly depends on which Linux distribution and which Kubernetes flavor your platform team picked years ago. Halfway through the lineup, we arrive at Docker. Docker is what most people picture when they hear the word container in the first place. Even though by this point in the stack, Docker is more of a developer experience layer than a runtime in the strict sense. When you install Docker Desktop or the Docker engine on a Linux server, you're installing Containerd, a runtime like runc, a daemon that wraps both of them, a command line tool that talks to the daemon, an image builder, a networking layer, a volume system, and a small army of conveniences that turn the whole thing into something a developer can actually use without reading a spec document. Docker is the gateway. It's how almost every working developer on the planet first met containers. And the muscle memory of typing Docker run is so deep at this point that even people who switched to other tools years ago still slip up and type it. The company has had a turbulent few years. The licensing changes for Docker Desktop pushed a lot of bigger shops to look elsewhere, and Kubernetes officially removed direct Docker support back in version 1.24. But on developer laptops, Docker is still the default in a way no other tool comes close to. It's the operating system of containers on workstations, even if it's not the runtime of choice in production anymore. Just above Docker, in spirit if not in scope, sits Podman. Podman is what happens when you ask a security engineer to redesign Docker and you actually let them do it. The headline difference is the daemon, or rather the lack of one. Docker runs a background daemon as root, which is a giant target if anything goes wrong. Podman ditches the daemon entirely. Containers run as child processes of your shell, owned by your user in your user namespace, with no privileged daemon sitting in the middle. Rootless containers actually work properly. The command line interface is deliberately almost identical to Docker's, to the point where you can literally alias Docker to Podman and most of your scripts will keep working. It groups containers into pods, the same way Kubernetes does, which makes the mental model line up better with what production actually looks like. It's the default container tool on Fedora and RHEL, and it's quietly eaten a huge amount of Docker's market share inside enterprises that care about security and licensing. If you're starting fresh on a Linux server in 2026 and you don't have a specific reason to need Docker, Podman is probably the smarter pick. Climbing higher, we run into a category most people don't think of as container runtimes, but technically are, the sandboxed runtimes. The most well-known is gvisor, which came out of Google. The pitch here is that a regular container shares a kernel with the host, and if anything in that container manages to escape, it has direct access to your host kernel. That's a bad day. gvisor sits between the container and the kernel and implements a user space kernel of its own, intercepting system calls and handling most of them itself before they ever touch the real kernel. The trade-off is performance. You're adding a translation layer to every system call, so workloads that are heavy on disk or network operations get noticeably slower. But for running untrusted code, like user-submitted functions in a serverless platform, that overhead is worth it. Google uses gvisor for parts of App Engine and Cloud Run, which means a meaningful chunk of the workloads running on Google's Edge are isolated this way. The sibling of gvisor in this tier is Kata containers. Kata takes a different approach to the same problem. Instead of intercepting system calls in user space, Kata spins up a real, lightweight virtual machine for every container, with its own kernel inside. So you get the developer experience of containers, where you ship an image and call something like kubectl apply, but underneath, each pod is running in its own micro VM, with hardware-level isolation. The overhead is higher than a regular container, but lower than a full virtual machine, and the isolation is real in the way only hardware boundaries can be. Cloud providers running multi-tenant workloads often use Kata or something like it, for the same reason hotels have walls between rooms instead of curtains. Speaking of micro VMs, this is where Firecracker comes in. Firecracker is not exactly a container runtime in the classic sense, but it lives in the same neighborhood, and you'll hear it mentioned constantly. AWS built it specifically to power Lambda and Fargate. It's a stripped-down virtual machine monitor written in Rust that boots a minimal Linux kernel in around 125 milliseconds and uses about 5 megabytes of memory per running micro VM. Think about that next to a traditional VM, which takes tens of seconds to boot and gigabytes of memory just to exist. Firecracker is what makes serverless economically possible. When you invoke a Lambda function and it cold starts in under a second, what's happening underneath is Firecracker spinning up an entire isolated Linux environment for your function, running it, and tearing it down. It's the closest thing in this lineup to magic, and the open source code is right there if you want to read it. Climbing toward the top of the lineup, we get to LXC and LXD. LXC is older than Docker, which surprises people. It stands for Linux Containers, and it's been around since 2008, building on the same kernel features that everything else in this video eventually uses: namespaces and cgroups. The difference is that LXC was built for system containers, not application containers. The model is, run a whole Linux distribution inside a container with its own init system, its own services, its own users, like a lightweight VM, but without the virtualization overhead. LXD is the more modern management layer on top, originally from Canonical, and now forked into Incus after some governance drama. If you've ever seen a Proxmox setup, the containers running alongside the VMs are LXC containers. It's a completely different way of using the same underlying kernel features, and it occupies a niche that the Docker-style runtimes never really touched. If you want a long-lived server that feels like a VM but costs almost nothing in overhead, LXC is what you reach for. Near the top of the stack, we have to talk about Docker Swarm, even though most people would tell you it's already dead. Swarm was Docker's attempt at an orchestrator. Take multiple Docker hosts, cluster them together, and let you deploy services across them with a single command. The experience is genuinely lovely. It's simple, it works, and you can have a real multi-host cluster running in about 10 minutes with no YAML files that look like they were written in anger. The problem is, Kubernetes happened, the entire industry standardized on Kubernetes, and Swarm got left behind. It still exists, it still works, and there are still small shops running production workloads on it perfectly happily. But if you start a new project on Swarm in 2026, you're choosing a road with very few other travelers on it. Which brings us to the top of the lineup. Kubernetes is not a container runtime, technically. It's an orchestrator that calls into a container runtime, usually containerd or CRI-O, to do the actual container work. But you cannot talk about the container world without ending here, because Kubernetes is the gravitational center the entire ecosystem is now organized around. Every other tool in this video either feeds into Kubernetes, gets compared to Kubernetes, or exists specifically because Kubernetes is too heavy for someone's use case. A real Kubernetes cluster has a control plane with multiple components: a network plugin, a storage plugin, a container runtime per node, an ingress controller, and usually a small constellation of additional tools just to make it usable day to day. Running it yourself on bare metal is a serious project. Running a managed version on AWS, Google Cloud, or Azure is the choice most companies make, because the control plane alone is enough work to keep a small team busy. You might never operate Kubernetes at home, but if you walk into a job at any company over 100 engineers, the odds it's running Kubernetes somewhere are close to a coin flip and climbing. It's the tool you reach for when your problem is genuinely big enough to justify a tool this big, and a sizable chunk of the pain in the industry right now comes from companies running it when their problem isn't. The thing that ties every runtime in this lineup together is a single, quiet observation. The entire container world is just different opinions on how thin the layer between your code and the Linux kernel should be. Runc is almost no layer at all. Kubernetes is so much layer that it has its own consultants. Everything in between is a bet on how much convenience you want in exchange for how much complexity you're willing to carry. Let us know in the comments which runtime you're actually using day to day, and what category you want us to break down next. Thanks for watching, and we'll see you in the next one.